Okay, welcome everybody. This is Statistical Inference. I think you know which classroom you're in. So I think you know what time it is, so we can skip that part on the syllabus, but I do want to kick things off not quite so dry and just going to talk about inference for a couple minutes and talk about what we're going to be studying, what we're going to be learning, and what the basis of this course is. Does anybody know what stat inference is? Let me just ask you a different question. What is inference? This is just a word. We use it commonly. It's not a technical term. So it could be applied technically. But you know, there are terms that we hear sometimes on popular TV shows like CSI, and they'll talk about the likelihood. And there's really only one definition of likelihood, and we'll go through what it is in here, and they use it incorrectly on TV all the time. But inference is a different type of one. So people use that term all the time. What does it mean? Josiah.
It's a little bit like prediction, where we're working with something, with what we do know, to say something, to make like a guess or an educated guess.
So Josiah said it's a little like prediction, and I agree with that. Does anybody disagree? I mean, he left himself enough waffling room in there. It's not quite like it. It's a little like it. It's similar. I think of it as the flip side of the same coin of prediction. So sometimes you'll hear people say prediction and inference are totally different things. And that drives me crazy. They can't be totally different. So a good inferential model could predict well. A good predictive model might not infer well. So it's not guaranteed. So I'd say the direction goes in one direction, but they're certainly tied together. So something like a neural network might forecast for you very well, but they're hard to infer what's actually going on. And so I use that in a non-technical sense, that term inference. So kind of like prediction. Anybody want to add something to it? I like classes like calculus, because you say, hey, what's calculus? And you know what it is. Hopefully you know what it is. So we won't have you define what calculus is. So what is this? This is the whole thing in stats. This is it. This is almost the whole thing, I should say. So this class is the entire field of statistics, in some sense. It is the baseline for everything that statisticians do. But we still haven't answered the question, what does the term inference mean? So just this. Should we get a dictionary? Do you guys know what this word means? That one might be hard to define. This is the easiest word in the sentence. Somebody else have to. Shake off the comments. Like it'll be.
When I think of inference, like I immediately just think the word infer, and so I think it's kind of like Josiah, but I think of like just to make a guess based on context clues, maybe.
I like that. I like that. So it's like making a guess. So it's a guess, but it's not any old guess, especially when you couple it with the term statistical inference in there. And so it's a conditional guess. Conditional on what you've seen before. So you see something, you're going to do something with that stuff that you've seen. You're going to try to guess what the actual model is. So you're going to have a guess at the things you don't know in your model. And maybe you could extend that to forecasting. If I knew what the model was, then maybe I could use that to forecast. And those things are definitely coupled. And we might go through a little bit in forecasting in this class, but mostly we'll be dealing with inference. In my Bayes class, which is a specific type of statistical inference, we do a lot of forecasting. And so the forecasting is definitely related to learning the model, which is inference. So they are tied together. But I like this. It's a guess, but it's an educated guess based off of what you've seen before. So it's a guess based on data. And statisticians always do something in particular. So our inferential models have a particular flavor to them. So what do all inferential models, statistical inferential models have in common? What do we do in stats? It's not the only thing going. There's been other fields that have evolved. Chaos theory, fuzzy logic, so determinism, differential equation forecasting, learning dynamics. So those aren't statistical. So what's the statistical component? Does anybody have the book? So it's Cassell and Berger. We'll look at it in a minute. How could I look at that for a second? So this is our textbook. This is Cassell and Berger. And I used to say it's not a great textbook, and I've changed my mind. I think it's a really good textbook, and what's hard about this textbook is it tries to cover all the bases of inference. And the mathematical forms that you'll use in each branch of inference might be different. So, which is kind of interesting. So you might be doing things like taking derivatives, setting them equal to 0, finding maxima by doing that. Or you might be integrating over something. So, might be doing lots of different stuff in coming up with a good statistical inference. But the first part of this book, the first 5 chapters, are on probability. And that's the prerequisite for this class. So the idea is that you've covered at least the first 4 chapters of this book, or a book similar to it. So this book is used all around the world, all around the country. Every grad program in the country uses this book. Some of them might use some more theoretical books, measure theoretic books, and I've seen those, and I have plenty of copies of them. One of my classes on inference was out of that, but I do like this book a little bit better that they skip all the measure theory. And that's what we're going to do in this class. So we're going to be picking up in chapter 5 on this book right here. But a statistical inference is a probabilistic inference. And so inference in some sense is the flip side to probability as well. And so we need to know the rules of probability, but probability is not statistics. Probability are just a collection of mathematical rules, and hopefully you know what they say. We can write them down later if you'd like to write down Kolmogorov's axioms. There's different ways to phrase Kolmogorov's axioms, and they're all the same thing. So partial coverings, I don't know if you've ever seen that. We've kind of gotten rid of that stuff since the 60s. So there's a certain collection of rules that make sure that when we add things up, we don't exceed 1, we don't go negative, and things are additive in nature. They're infinitely additive. We can write down those rules as we go. But that's the prerequisite for this course, is to know probability. Does everybody know what Kolmogorov's axioms are? It's a good place to start. And if you have heard of them and you kind of remember what they are, I'd say go look them up at the end of this class and make sure we're all on the same page. We're not overly technical today. So inference is guessing based off of data. That's the idea. And statistical inference does it in a probabilistic sense. So we try to quantify uncertainties. So I used to like to say it differently, and I was like, oh, quantify our certainty. And it is the same thing if you adhere to Kolmogorov's axioms, because it's one minus the other. It's the complement. But I'd like to say what we're really doing is quantifying our uncertainties, because people like to forget that they're uncertain about things. There's certain levels of inaccuracy that we're always going to have to deal with. And we're going to have to quantify that as well. And we're going to have to come up with properties that tell us what those levels of uncertainty are, and how to calibrate them, how to understand them, and how to drive them down. And that's what this class is about. It's taking levels of uncertainty and driving them down so we can make better guesses and have higher probabilities of being correct. That's what this class is all about. We're also going to learn some of the ideals that statisticians study. We're going to deal with some of the conflicts that statisticians have. We're going to be dealing with all kinds of different problems, from computational problems to mathematical problems. We're going to be doing things simulation-based, and we're going to be doing it theoretical. We're going to be trying to pair those things together. And so I think that's what all good statisticians do these days. So this isn't just a theory class, but I would say it's about half a theory class. And then the other half is practical. And so I'll be teaching you tools along the way that'll help you to understand some of the theory, and some of those tools are actually applicable all by themselves. Anyway, you know my CV, this is roughly it. This is wildly out of date. in terms of what my interests are, but those have some of my previous interests. This is going to be your course webpage. It's right here. I'll write that down. It is www.apps.stat.vt.edu. So that's all the easy stuff right here. Don't forget this. Apps, dot, some of your browsers will take it without the www. And then it says /Lehman. And that's my last name. So, and that's how you'll navigate to this page. This is your course web page, and this is going to have all of your materials. So we will not use Scholar or Blackboard or Canvas or any of those things. And the reason I don't like to use them is because I've had to change 3 times already from Blackboard to Scholar to Canvas. It keeps moving my stuff around. So I like to keep a repository just on my web page. And so that's what we'll do, is we'll do that. Let me show you how to navigate this page. You'll go up here to courses taught. So it's that link. I know this is really poorly laid out. So I'm not a web developer. So this is going to take you to all kinds of classes that I've taught in the past. So I leave that up if you want to look. So some of them I'll teach maybe next semester. So I teach the Bayes class next semester. And if you want to go there and figure out what I taught in the Bayes class, you can even go to the schedule. I usually leave these up for until I teach it the next time. So if you wanted to see, like maybe there's some handouts or notes or something and you want to know more, you can go to one of my other classes. Your class is going to be this link, Stat Inference, the first one. And so here's the basic structure of the class. We can read through this a little bit later. But it basically says what I've said already. You're going to learn inferential methods for parameter estimation. You're going to learn underlying quantities in a model. We're going to learn about order statistics and their distribution, approximate methods, the delta method, computational methods, asymptotic methods. Asymptotics appear in the book in chapter 10. We won't touch chapter 10. I'm going to be sprinkling it in throughout the first 5 through 9. In fact, I'm going to be sprinkling in chapter 10 stuff in chapter 5 without you knowing it. I'll point it out. So we will study things like the bootstrap early on, so we have comparators. So I don't like talking about one topic at a time. I like to compare things to each other. So we actually understand what good means. So that's a relative term. So we'll be studying asymptotic methods. We'll be doing also Bayesian and classical methods and comparing those 2 things and trying to understand what those different branches are all about. So I approximate, this class is roughly about 20% to 25% Bayesian. And I would say Casella, George Casella, the author of your textbook, is probably about 50% Bayesian. I probably came here 16 years ago. It's my 16th year of teaching. So, and I was probably a 90% Bayesian then. And now I'm probably a 70% Bayesian. And so we'll moderate this sort of stuff and understand what you can do to mix and match some of these ideas. So there's some things that I do classically, because I know that if I did it in a Bayesian manner, I'd get about the same answer. And it would be more computational to get that same answer. And so I'll want to obviate some of that. And so we'll try to understand all this stuff. And then we're going to be going into interval estimation, which is the flip side of things like hypothesis testing. And when we talk about hypothesis testing, that's when my mood is going to change in this class. And I'll try to explain that, what it's all about. I'm going to try to give you the basic underlying principles of hypothesis testing. I'm going to try to tell you where the disagreements are, and then I'm going to let you know what I'm going to test you on. So I know it's going to be a lot, and it's probably going to take some of you 5 more years after this class to really make sense of this big divide on hypothesis testing. And so we'll be looking at the tip of the iceberg, I'd say. And if you want to know more, in my Bayesian class, I also compare to classical methods. So I go the other direction. And I start enhancing some of that lecture. I'm not going to dwell too heavily on what exactly I do in hypothesis testing. I'm going to tell you what most people do, and I'm going to tell you what it means and what it doesn't mean. So, and what they're guaranteeing and what they're not guaranteeing. Now, just keep in mind there's different types of tests. And while some of the properties of those tests might be the same, some of the properties of the tests might be different. And we want to understand what are the differences. So we also will do a little bit of MCMC. I'll be giving you some extra credit problems along the way as well. So if you perform poorly on a midterm, you'll have ample opportunity to make up for it in an extra credit homework assignment. So I would say my typical class, at least half of you get solid A's, and that's at least half. So I'd say it's probably around 75%. And then the rest of the class, maybe A minuses, B pluses. But if you want to knock it over and get the higher grade, if that's important to you, I'll try to give you opportunities to do that throughout the class. Okay, similar to my other class link, there's a schedule button. So you have to be in Stat 5114 to be able to access this schedule. So you'll go to 5114 Stat Inference, hit schedule, and this is my entire schedule from last semester. I'll be taking this down after the weekend. So if you want the handouts or the materials or anything like that, there it is. And there will also be a permanent record of this on YouTube from my video camera. So I'll try to make that big enough that you can actually zoom in and look at this. But you won't be able to click on all these links. So this is some MATLAB code. We'll look at this code in the next day or two. And these are the assignments that I'll be giving you. So if you want to get ahead on the problems, these are all from Casella and Berger, the book that we just looked at. You can just write these down and start working at them and chip away at them. So there shouldn't be any secrets. If you want to get ahead, here's your opportunity to do it. I will point out, Chapter 5 is a lot of probability theory still. It's a bit of asymptotics, central limit theorem, order statistics. So we'll be covering about through 5.3. And then we'll turn the page. I love the other stuff that goes on in Chapter 5. Simulation methods, transformation of variables for Monte Carlo, things like that. So we won't be dealing a lot with that, but I will allude to it in some of the homework problems. So if you want to get started on your homework, you can start reading chapters 5.1 through 5.3 of Casella and Berger and start chipping away at these problems. So I don't have a due date for you. So there's nothing technically being assigned right now. It's possible I'll change a little bit of this, change some of the assignments along the way. There's some different homeworks down here. The delta method compared to the bootstrap compared to Bayesian methods. So while we get out of Chapter 5 and just into Chapter 6, we'll be comparing 3 different branches of statistics. Asymptotic computational methods, I would say purely computational methods. So the delta method is an asymptotic method. The bootstrap is a computational method on resampling. And there's a Bayesian technique that I'll show you as well. And they're all going to be trying to solve the same problem, and you're going to be simulating everything. So if you want to have a look at that and start getting ahead and figure out what you need to program in the future, you could download that assignment. So you can just click on that. Boom, there it is. This isn't going to come for another month or so. So we need to get through the material. If you want the LaTeX code as well, I also include that for you, so you can click on that and then just download the LaTeX code. So you don't have to LaTeX your assignments up, but I do need them legible. I don't need them scribbled all over. I don't need your rough drafts. And probably the best way to organize all of this is to use something like LaTeX. But it also is time consuming. So if you're running out of time, you don't need to do that. It's not compulsory. But what I've always found is when I do my homework and I LaTeX it up and I make myself a solution key, I can never forget that problem. So it's usually the second time you write down a solution to something you already know that it ingrains itself. So there's no secrets to anything in this class, or anything at all. It's all practice. And the more you repeat, the better you get something. So the best thing you can do in this class is to work every problem in Casella and Berger. That's impractical. You won't be able to do it. Some of those problems are actually particularly difficult. So, but the secret to being good in this class is working the problems. If you're sitting there just reading the chapters and going, I think I get what they said, flip to the back and see if you can apply it to new problems. See if you can do the example problems as well. So the examples in the book, sometimes I sprinkle those into midterms. and check to see if you're actually reading your book. And it'll identify for me real quickly where the problem is. So make sure you're reading through all the examples, but also working those examples and understanding what they cram into these small paragraphs. So it's always nice when they're like math, 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 but sometimes that small paragraph right underneath where they say a bunch of stuff, there's a lot of calculations in that stuff. So you should be working through all of that. We'll go into p-values later in this class, so there'll be some statements on p-values if you want to get ahead and read where the ASA, the American Statistical Association, is on p-values. You can come down here and read their statement on the ASA statement on p-values and the BAS statement on p-values. And we'll be going into that when we get into hypothesis testing. It's like most committees. So they don't come to any strong conclusions. They just point out there's problems everywhere. Chapter 7 in this book is estimation. That's the easiest chapter. It's the most like calculation-oriented chapter, I should say. It doesn't have a ton of concepts going on. The concepts are pretty easy to implement. So I would say chapter 5 is a little bit challenging, just to shake off the cobwebs. Chapter 6 is about principles, and so that's going to be a lot of theory and guiding lights and proofs, things like that. So things that we can apply later on, things that spur debates. And chapter 7 is relatively straightforward. Chapter 8 is hypothesis testing. Chapter 9 is interval estimation, and if I need time at the end of the class, I'm going to take it out of chapter 9. So we're not going to race just for the sake of racing. Any questions so far? Next time, we're going to fill out the syllabus so that we all have the same syllabus. So you can start reading through this. I think what you're mostly interested in is what does the grading look like? So we have 2 midterms and a final exam. So I've broken them down to be 25, 25, 25. So I'm not going to do the thing where you got 70% all on your final, you miss a problem, you drop 2 letter grades. So it's not going to go like that. These will be cumulative. Everything in life is cumulative, especially in math type classes. And the final exam date is already posted for you. So if you go back to the syllabus, right here, that's something that I've already filled in. So that's going to be May 9th, 7:45 to 9:45, and that's on the AM side. The lucky part is that we're waking up early anyway this semester, so we're already well prepared to manage this. So I am planning on doing an in-class final exam, which will help at least the PhD students in here prepare for their qualifying exams. So I think it's important that we do a lot of testing in this class, just to point out where you need to hone your skills. So that part's already filled in. I don't have dates for the midterms yet. We're going to have to agree on those together. So next time what I would like is everybody come in with their calendars and all of their restrictions, and I'm just going to poll you guys until we get midterm dates. We will be doing those in class, and they're going to be very homework-esque. So if you're well prepared on your homework, the midterms shouldn't be overly difficult. So I'll try to make the homework assignments difficult enough so that they prepare you well for the midterms. Those will be in class, so they're 50-minute midterms. And so the whole idea is to know things quickly. So I won't be giving you excruciating calculus problems where you're like, geez, I need to know partial fractions all of a sudden. We won't be doing that. So I won't be doing anything overly tricky. You might have to integrate some polynomials or something. In class or for homework, you'll have harder integrals to do, but on midterms, I don't think so. So bring your calendars next time and we'll fill out what dates those are. This will be in class, this class, in our scheduled time slot. The university picks our final exam dates for us, so I can't move those. I've tried to move it before, and it is an absolute disaster, and I promised myself to never do that to myself again. Okay. My office is 401A Hutchison, so you know where Hutchison is. So I'm over in the back corner that way. You can swing by anytime. I'm always happy to answer questions. If you see me in the halls or something like that, feel free to ask me a question. Probably in the last 16 or so years, I've probably told people maybe a dozen times, I don't have time right now, but I'll get back to you. So chances are I'll have time for you. Let's see, we're gonna also be doing bi-weekly review sessions. These are not compulsory. So, but instead of just open office hours and leaving you just hanging with that, sometimes it's nice to bring everybody together and we can ask homework questions or other questions or miscellaneous questions or extensions or stuff from the past. Maybe you say, I don't really understand where that Jacobian term comes from in transformation of variables. Could you explain it to me? So I'm not going to do it in this lecture, but I'm happy to do all of that stuff. I can give you my intuitive explanation, I can give you a mathematical explanation, and go as deep as I'm able to go on problems. We'll figure out how far is right, but that has a lot to do with you guys. So they'll be about bi-weekly review. They'll coincide with weeks that have homeworks due. This is an approximation, so it won't be every other week. We'll also have a Slack page as well, so that we can message each other. And I'll be setting up the Slack page for this class. I'll be sending you the links for the videos, the YouTube page, and I'll be sending you the links for the Slack page as well. So if you're not enrolled in the class and you want to be part of all of that, I know I have at least one auditor in the class, just send me an email and say, include me on all the messages and I'll get you included. So be on the outlook for an email from me in the next day or so, and it'll have all the resource links for the class. Prerequisites, probability. And you know what a for loop is and a while statement. And you've used some software before. I'm going to be using MATLAB throughout this class. This is a big engineering school. Most statisticians use R, so I'm going to mix things up a little bit. R and MATLAB are not that dissimilar. So if you want to use Perl to code up all your stuff, you can. If you would like to use assembler, you can. But I wouldn't recommend it. I'd use something like R or MATLAB, something with graphing facilities built in. So computing, something like MATLAB R, for loops, while statements. You know what the grading looks like? And I'll go through this stuff next time, academic honesty, but it basically says you're allowed to work together, but you are not allowed to plagiarize each other. And so your work should be your own work, even on projects. If you feel like you might be cheating, you are. So, and if you have any questions about that, come and ask me, and I'll tell you. Even if you have plagiarized and you're like, can I turn this in? We worked together, I wrote this, my friend wrote that. Are these sufficiently different? And you'll probably know the answer to that already, but if you're concerned about it, you can come and ask me. There aren't a lot of opportunities in here to be academically dishonest. If you think your work has been graded incorrectly, this has a whole bunch of rules in here. What it really says is just come see me. So our TA is J. Young Lee, so he's one of the best TAs in the department, so we're in good hands. I'll be asking him to set up Zoom office hours so that you'll have some contact points and all kinds of different mediums. You can meet me in my office, you can come to review sessions, I'll get us a room. We'll also need a time for that review session. And so I usually aim for about 5:30, and I can't get a room any earlier than that. So I don't know if you've noticed, all our rooms are filled during the day, for the most part. And so next time we'll also be looking at our schedules for our review sessions. I personally like, should be right here. I personally like Thursdays for review session because we have colloquium. After colloquium, we go out, and then I like to come back here. I'm already on campus, and we can do the review session. If Thursday doesn't work for you, I don't mind doing it on Monday, Tuesday, or Wednesday. I don't do them on Fridays for obvious reasons. Monday's also not a good day, so try to be generous. If we need to push it to 6 o'clock, that's fine with me as well. These can last up to 3 hours, and you can come and go as you please. So you don't have to be there. What I'd like you to do is post questions to Slack, and there'll be a channel on the Slack page that says review questions. And so I usually ask 15 minutes before the review starts up, please have your questions in there. But you can also dynamically ask me questions throughout. But it's nice to have some questions, so if all of a sudden 5 of you have questions that overlap each other in a particular way, I can try to devise an explanation that builds in that overlap. So we'll probably have to get through one iteration before we all feel comfortable with this. Okay. There's supposed to be ample opportunity to meet with me or the TA to get all the help you want. So I would recommend not getting behind in this class. It's very hard to catch up. Any questions so far? Okay, primary reading, Casella and Berger. So I'm going to be asking you to read the chapters as we go. I'm not going to be telling you all the time, read chapter 5.4 or something like that. So I assume all of us are graduate students, we're professionals already, and so we have the book in front of us, we know how to read it. So don't not read your book. So even if I don't say a section is important, it's good to fill in all that stuff. That's why we're really here, is just to understand it all. It's not for all the testing. Okay, we'll come back, touch up the syllabus next time, but remember to bring your schedules. Once we lock in these dates, they're locked in. So if something happens and we have a lockdown, or who knows, we'll improvise. I can do take-homes, things like that. If you're critically ill, let me know in a timely manner and I'll work with you as well. So make sure everything functions properly. Okay. So I think that's enough of that for right now. Let's start with an inference question. So this would be a typical sort of inference question that we might ask in this class. So I'm going to give you a little bit of notation. Here's an example. So what I'm going to first say is I have some data points, xi's. These are realizations. They're actual data points. And they come from some distribution. And we write that like this. So this says distributed as. So these data points follow some distribution. And I'm going to give a distribution an actual specific name. So this is the uniform distribution. I usually either just write U or Unif or something like that, but I'll spell it out for the first couple of these. So it's going to be uniformly distributed, these xi's, and these are going to be some specified values. So this is all the stuff you've already seen in probability theory. We use the same notation. So I'm going to say these xi's are uniformly distributed between 0 and theta. And so theta is a parameter. Nothing complicated so far. Everything is one-dimensional in this problem. And so the idea is we don't get to observe this. This is hidden from you. For some reason, we might get to know that the distribution is uniform. In real problems, you don't need to know that. You have to figure out which family of distributions your data lives in, and then you have to identify all of the unknowns. So in this class, the fiction is going to be, we always know what distribution it came from. So I'm not going to have you figure that out along the way. So we're not going to be doing what we call modeling. So there is a good class in this department, hierarchical modeling, that goes through that all day. But really, you want to just work on a lot of projects and start doing your own modeling, and it's a trial and error sort of thing. So modeling is not, you just write down a model and you go with it. Usually you have to check all your diagnostics, make sure you've got the right model, maybe you forecast, and see if your model forecasts well as one of your diagnostics. So kind of like your prediction layer to all of this, to figure out if you even have the right inferential model. We won't be doing any of that. We're just going to know this part. What we're not going to know is the underlying parameters in this class. So the idea is you need to learn this or infer. And that's our word. So guess at it. We're not just going to guess willy-nilly. I'm not just going to say, I don't know, I think it's 7. So I have no basis for making that claim. If I asked you a question like, why do you think it's 7? Why is that a good estimator? You'd need to be able to answer it. And right now, I don't have any justification for saying the number is 7. So usually we write something like this, IID. This means simple random sample, if you don't know. So when you're reading through chapter 5.1 and they say simple random sample, they mean IID. So that's the same thing, they're synonyms for each other. What do those letters stand for?
Independent.
And identically distributed. Now, it's important that both of these things go hand in hand. So data itself is not independent of each other. Data given the model in hand is independent of each other, possibly. So if I don't know theta, if I take this away, then all the xi's are related to each other somehow. And I could probably forecast future xi's by looking at previous xi's. If I knew theta, that wouldn't help me. The previous data wouldn't help me to do anything. And so what this is saying is that I'm sampling from the same distribution every single time in exactly the same way. That's what it means, at least conceptually. So as a picture, I might have n data points. So we'd say something like I goes from 1 to n. N is your sample size. Let's say n was 10. What that would mean is that there's some underlying distribution between 0 and theta. And I've got 10 uniformly distributed data points between 0 and theta. And so what that might look like is this. Okay. So it's not going to look like an exact lattice. So it's not going to be uniformly spaced exactly. What it means is that for each one of these data points, my whole collection, and these data points right here, I might represent my cap x. I might say I've got x1 to xn. And so this is my entire collection of data, and it's comprised by 10 data points. So this would be a 10 right there. What it means is that every time I sampled one of these data points, I reached into this distribution and I sampled with density proportional to the height of this curve. Now this curve doesn't look very curvy, it looks flat. It's still a curve in my book. So, and the density is exactly the same height at every point. So what that means is that I'm equally likely to sample a point at each location between 0 and theta. So that's what it means to sample in an IID manner. So the question I have for this, if we understand all of that, and hopefully we do understand all of this, just real quickly, what's the height of this curve? 1 over theta. How do you know?
88 to 1.
It integrates to 1. So all probability densities integrate to 1. They're always positive. All of that good stuff that Kolmogorov already tells us. So we know the height of this thing. It's 1 over theta. It's a constant. So we can't actually write that down because we don't know what theta is. All we get to see are these 10 data points, and we get to figure out what theta is. Let me just ask you a question. If I told you, like you didn't know this, let's say that was 10 right here, but you didn't know. So, and let's say this number was right here, 9.8. That's my biggest number in the whole collection. Would a good inference for theta be, theta might be 5? Absolutely not. So, because I've got a data point that exceeds 5, and theta is the upper limit. So that would be a really bad inference. So if I saw 9.8 as my biggest number, I probably know theta is bigger than 9.8. So that would be our first step in guessing at theta. I'll just ask you guys a question. And you don't have to be mathematical about this. You can just use your intuition. But here's my question. How would you estimate theta? You don't even need to have a good answer right now. Later on, we'll be comparing probably the answers we come up with. But somebody just take a stab at it. How would you estimate theta? You get these 10 data points right here, this collection, and you're going to use it to estimate theta. Anybody want to take a stab at maybe an estimator for theta? Not 5. What would you do? Somebody comes into your office, says, I'll give you $1,000 right now if you can be within plus or minus 1 unit of theta.
If you take your 10 data points, you could average them and double it. So you assume your average is roughly.
Yeah, so what Brendan said is he knows what the average should be the middle of the interval, and that's going to estimate the middle of the interval. So this might be x bar right here. X bar is just sum of the xi's divided by n. Sum goes from 1 to n. So I might come up with x bar and one estimator for theta. We usually distinguish this from the truth by putting a hat on top of it so that we're not saying that the truth is this number. This is just our best guess. And so I'm going to take this 2 times x bar. So x bar measures the middle, 2 times it brings it over to the endpoint. Good estimate. So anybody have any other guesses?
We can calculate maximum value.
Maximum value. So you might take just this value right here. I'm going to give it some notation. I'm going to call this the max right here. And I'm going to give this, so my max of my collection of x's, all of that stuff, I'm going to give this some notation. I'm going to call this xn in parentheses. This is the notation that your book uses for the maximum order statistic. So x1 in parentheses is the minimum. x2 in parentheses is that second biggest number. xn in parentheses is the biggest number. So they're the ordered numbers. So we'll reintroduce that notation, but you might say the maximum itself is a good estimator of theta. So here's another guess, 2. Theta hat is equal to xn. Any other guesses? Any other potential inferences? Yeah, we can do this all day long, right?
We can take the likelihood, which is going to be peaked at the max, but that's going to decrease, and we can find the area where 50% of the probability is below, 50% of the probability is above, and use that as the estimator.
Oh, so you would take the median in some sense and then map it over.
Yeah.
It's interesting. So you take the max, you know what the maximum likelihood is. It's the max, xn, and then you do.
And it's 0 below the max, because you know it couldn't be.
Okay,
and
so
it could be some value lower than the max. So you could take the median of the likelihood.
I see. Are you saying take xn and, okay, let's work on that. You can tell me what it is. I can code it up for you once you explain it to me. We'll look at how all these perform against each other. Let me give you another one. I didn't quite understand exactly what Josiah says. We've got 1 minute, so let me just write down another one. You can explain this to me after class. But here's another one. I can take maybe the max, and I could subtract the min. So this is the range. And that's definitely an estimator of theta. It's not a very good estimator. x1 is going to be approximating 0 in some sense. So I'm subtracting off some approximation of 0. We could probably already figure out this is probably a better answer than this. The question is this a better answer than that? Let me ask a quick question about this. What properties do we like about this?
That one, the first one is unbiased, whereas your maximum likelihood is going to be
You guys are pretty good. So this is unbiased. That's a statistical property. What does it mean?
That the expected value for 2x is equal to theta.
That means the expected value of 2 times x bar is equal to theta. Is this estimator biased? It obviously is. So this one is biased, that one's also biased. This one is biased because it always lives to the left of theta, guaranteed. The more n I have, the more sample I have, it gets closer and closer, but it's always to the left. So this one is biased. Is this starting to give us some clue as to which estimator we might like best? Do we like that estimator better or that one? You guys like the maps? Or you like this one? You like the first one? Let me just ask a quick one. I'm going to poll you and then we'll come back with this next time and do some simulation and check out and see which one is better. How many people like, let's get rid of this one. We already know this one's better than that one. If you don't know that, we'll simulate it and check it. But we don't know maybe off the top of our head which one of these two is better. How many people like number 1? Raise your hand high. I just want to count for a poll. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Like this one. How many people like number 2? Better than number 1? It was your estimator, right?
It wasn't my estimator. I want to know the sample size before I...
Okay, gotcha. Yeah, that's an interesting question. Maybe it depends on the sample size. And sometimes inferences do. Does anybody like 2 better than 1? I do. So, and we'll figure out why in this class. But that is what this class is about. So I'm going to put down 1 right here. 1 to 16. And so, of course, yeah, maybe sample size has something to do with it. So, but we need to check all these things. So this is a particular estimator. It has a particular property. This estimator doesn't share that property, but there's more to the game than just biasness and unbiasedness. There's also things like stochastic variability. How variable is this estimate in the first place? How much does it wiggle around? And is this estimator more stable and on average closer to theta than this one? So it's possible that this could be closer than this one for a particular sample, but on average, this one tends to be closer. And we'll come back through with the simulation, study that a little bit. We'll be building up the theory to be able to answer these questions. Which properties do we want and how do we defend our estimators? And in a nutshell, that's what the whole class is about. Thanks, you guys. That's it for now. I will be sending you an email with all of the information about the class. Wait for tomorrow for that. And what my plan is with the videos is to video every class and post them at the end of the week. What I have been doing throughout the pandemic is posting them at the end of every class because not everybody can be here, but I don't want to discourage attendance because that's one of the best ways to get ahead in this class. So I'm not going to be posting them 5 minutes after. The videos are no substitute for in-class stuff, and the best part of the class is you guys. So communicating with each other, and that's what I'd love to see. So at the end of the week, I'll be posting videos. Stay tuned for an email, and I'll see you on Friday. What were you thinking, Josiah? You almost wanted to say that. I feel like people might recognize So 50% of the probability. So if